So good afternoon once more. This afternoon we begin with STP lab. We want to see how to configure STP lab. It is lab 3.1. Are you able to see my screen? Hello?
Yes.
Yes, you can see us.
Okay. Sawa. So lab 3.1, configuring STP. I really don't want you to do it as I do it because I'll be a little bit fast. You can do it some other time. I'm recording it so that you can follow through much later. Right now, I just want to emphasize some of those theoretical principles about STP that you've learned through this particular lab. So the objectives for this lab is to enable, be able to enable and disable STP, change the STP mode, change the bridge priority to control the root bridge election, change the port priority to control election of the root port and designated port, and to also change the port cost to control election of the root port and designated port. So we're going to learn all that here. The last one here, I think, was a mistake. We're not going to configure any edge ports, only RSTP support edge ports, as you're going to learn in the next topic. So this is the topology. So really, in this particular example, we are having two switches, S1 and S2, and as you've learned in the theory, we have to implement redundancy, especially at the aggregation and at the core layer, so that to provide backup in case one link goes down, the other link still works. The problem with that is switches can easily form loops. If a switch receives a broadcast packet, it's gonna forward it through all the interfaces other than the interface in which that packet was received. And therefore, if this particular frame gets to the switch is gonna forward it out through this interface again. It's gonna come back here, it's gonna come back here, this guy is gonna again send it here, and that is how loops occur. And therefore the main purpose of STP is simply to prevent switching loops by blocking some of the ports, and that is what really we are supposed to see in this particular example. So let me implement that in ENSP. So in ENSP, on the left column here, you can click on the next icon there under this area to reveal the switches. We're going to use the S5700 switch because it offers 2400 base T Ethernet interfaces. So we need that. So I'll simply click on that and then drop one there and drop another one. I'm also gonna rename this into the label. It's just a text label into S1, and this one into S2. So according to the topology, they've been connected on gigabit Ethernet 009. So on S1, 0009 on S2, and 0010 and 0010. Then after that, I'm going to just align my topology. So horizontal align. I'm also going to align these labels a little bit here. Okay. So before I even start the switches, let's go back to, sorry, let's go back here. So I don't want to go through the scenario there. The first step one, they're telling us to configure STP and verify the STP configuration. And what they're telling us here is that we should disable all the other interfaces on the switch to shut them down. But their starters are already down because we've not interconnected them. So we really don't need to do that bit. We only need to begin here. So in the lab, S1 and S2 are connected through two links and STP is used. So enable STP on S1 and S2 and set STP as the root. So to enable STP, we use the command STP mod STP on system view. Then to make S1 the root, we can use the command STP root primary. On the other hand, we want to configure S2 as the, so this STP root primary will make S1 to be the root bridge. So as we learned in the theory class, STP will create an inverted tree where one of the switches is going to act as the root bridge. So this command STP root bridge will make S1 the root bridge. And then STP mod STP on S2, then STP root secondary. So it will ensure that this guy becomes the secondary bridge. Okay, so let's do that first. So let me go back to ENSP. Now, before I start the switches, I want to do data capture here so that I explain a number of things. Oh, I have to start it first. So let me start them. Okay, so once I've started them, I can right click on this interface here. Still taking time to start, just a moment. In the meantime, I can double click on S1 and S2 to open their interfaces. Now the interfaces are up, so I can right click on it and click on Start Data Capture. So when I click on Start Data Capture, it will open up Wireshark. I just want us to see a few things on Wireshark. So you see already, immediately I start the devices, the two switches. You can see that we have some packets that are being captured. You can see 8, 9, and so on and so forth. And if you look keenly, you can actually see that it's for STP. And if you go even deeper, you can see that it's MSTP. In the theory class, we learned that the default STP mode is MSTP, multiple spanning tree. And therefore, these packets that are being captured here are simply MSTP hello packets. And if you look at the timing here, you can see that the hello packets indeed are being sent after every 2 seconds. After every 2 seconds. And the hello timer is one of the common hello STP timers actually. Okay, so let's go ahead and configure S1. So the first thing I'll do is to go into system view. Then I need to rename this. So system name S1. I like renaming them first. So let me also rename S2. So S2. Then we go ahead now in S1. Let me just clear. Here in S1, we need to enable the STP mode, to change the STP mode. So if I do STP mode, then I use complete help. You can see that if I do a question mark, those are the available STP modes: MSTP, RSTP, and STP. At this level, you're only going to learn about STP and RSTP. MSTP is covered at HCIP level and also at HCIE. So we specify STP as the STP mode. If I do that, let me go back to Wireshark. I want you to see if I change the mode. Okay, so if I change the mode, you can see that now we've changed from MSTP to now STP. If I open up this, you can see that the protocol identifier, remember the protocol identifier, PID, field on the spanning BPDU header. So you can see that it's actually, the type is actually STP, spanning tree protocol. So it's no longer MSTP. If I click, for example, on this one, you can see that it is multiple spanning tree. the protocol version is multiple spanning tree, but now we've changed it to STP. So let me go back. Okay, so let's also change, make this the primary. So STP root, that's the command, primary. So STP root primary, I can use the tab to autocomplete. Then here, we go ahead and do STP mode on S2, STP. Then after that, we do STP root, STP root secondary to make it the root bridge. So now S2 is going now to act as the root bridge. Okay, so let me clear there and also clear here. So let's go back to our guide. So now, after enabling STP and changing, specifying the root bridge and the secondary, we can now use the command display STP brief. Display STP brief. So let's do here STP display on S1, display STP brief BR. So if I do enter, we can actually see that both ports, both gigabit ports, have the designated role. You know that anytime all the ports of a switch have the designated role, it actually means that that particular bridge is the root port. And when you're on designated port, when you're a designated port, then your state, your STP state is forwarding. So you remember the other states for STP. We are actually going to see them in a short while. So let's also do the same on S2. So here we also do display STP brief. So if we do that, we can actually see that on S2, the role for 0009 is the root. The role for 0010 is alternate. So alternate on discarding state, root port forwarding, because the root port offers the shortest path, RPC, to the root. So to avoid having a loop between S1 and S2, STP is actually blocking. Is actually blocking this particular interface, gigabit Ethernet 0/0/10 on S2. So really, that is what we needed to understand there. Now let's go ahead and proceed to the next step. So we can also use the command display STP interface, then the name of the interface and the number of the interface, in order to see a number of stuff there. For example, whether the state of that particular interface and the role of that interface, the port role. We've already seen it using the previous command, but this command is also important. So let's try it. So display STP int, then let's do G0/0/10. So let's see. Now at the top here, we just have information about this particular bridge, about switch 1, but where you get information about the port is from here, so this is information about the port. So one thing that we were supposed to note is that the state of the port is actually in forwarding state. The port role, because this is a root bridge, the port role is designated port. You remember the port identifier? So the port identifier is formed using the port priority and the port number. So the port priority, the default port priority is 128, and the port number here is 10. So if I do, so you can see here, so this was the other thing that we were supposed to see, this one. So this is a designated port, and you can see the port ID. So this is the port ID. So 128, which is the port priority, 10, which is the port number. So that is what we call a port ID. Then this is also the designated bridge or route bridge. So the route bridge will have the priority for the route. Here it is 0 because we've specified manually using the command STP route primary. So that's why the ID here is actually, the bridge ID is actually that. Then this is the bridge MAC address. So the bridge MAC address together with the bridge priority makes the bridge identifier, the bridge ID. So we're also going to see that in a short while. Okay, the list here is quite long and there's a few other things. To get out of this list, I can simply do Control-C. So I can also check the same information, for example, about gigabit Ethernet 0/0/10 on S2 by doing the command display STP interface G 0/0/10, like that. So if I do enter, we can see that we are on 10 here. We can see that indeed the state is discarding, the port role is alternate. The port priority is the default one, which is 128, and the port ID is that. We can also see the cost. The cost for this particular port is actually 20,000, and you can see that the default path cost that is used is actually, port cost that is used is the .1T standard. And for the .1T standard, if it's a gigabit Ethernet, if it transmits at 1,000 Mbps, then the cost is going to be 20,000. So we've not configured any cost. So we are simply using the default cost, which is the .1T cost. Okay, so let me do Control-C to exit that list, then go back to our lab guide. So the port times, I did not show you the port timers, but it should be somewhere. Let me check whether it's there. I can use the up arrow to access that command again, then enter. Then I can just do enter till I see the port time. Yeah, it's here. Okay. So the port timers, you can see it here. So we have the hello timer, 2 seconds, the maximum edge timer, which is 20 seconds, forwarding delay, which is 15 seconds. So those are some of the timers that have been configured on each of those ports. Okay, let's see what else we have here. So I think I've already mentioned all of that. So now we want to control the route bridge election. So who's the route right now? So let me use that command again. In fact, I can just do display STP. If I do display STP here, so right now I'm in S1. So if you look at this, so this is the bridge ID. So the bridge ID is the bridge priority, which is 0, and the MAC address for that particular bridge, which ends with 08AE. Then here you can see the route bridge. So when the route bridge has the same value as what we are having here, it simply means that this device is the root. In fact, if I do here display STP, you can see the difference. So here you can see that the bridge ID, the bridge priority is 4096, which is the default, and the MAC address ends with an 8A. But if you look at the CIST route here, CIST is for Common Instance Spanning Tree. It's not something that you learn at this level, but you're going to learn about it. In the meantime, just know that this is what specifies the bridge identifier of the route bridge. So you can see that indeed the root bridge is device A because its MAC address was ending with AE, if you can remember. So this guy is not the root. S2 knows that the root bridge is device A. Okay, so now we want to control the election.
Very, hold on,
Yes.
please. Can you come up again that concept?
Okay, I'm just saying that using the command display STP, we can be able to know who the root bridge is. So the root bridge is elected using, of course, the bridge identifier. The one that has a smaller bridge priority will be elected as the root. If the bridge priority are the same, it goes on to compare the MAC addresses. Whoever has the smaller one gets selected as the bridge. But in this case, we configured this device S1 to be the root bridge using the command STP root primary. So that's why the bridge priority for switch 1 is 0. The MAC address is AE. So the combination of these two, the priority and the MAC address, forms the bridge identifier. So what I'm saying is that this field here is the one that is used to show you who the root bridge is. So when this value here is the same as this value here, it simply means the switch where you've entered this command display STP is the root. So you can see on S2, they're different. The value here, and the value on the fourth row, they're different because S1, this device is not the root. So sijui kama umenielewa hapo. Is that clear?
Yes.
Exactly. So it just means that. So now we want to change. We want to alter the election so that S2 can become the root and S1 can become the secondary. So let's go on. So what we want to do in order to change the election, in order to alter the election, we can alter the bridge ID. We can alter the bridge ID. We know that by default the bridge ID is 4096. So the one that has a higher value of the bridge ID has a lesser priority of becoming elected. So we want to configure S1 with a higher value of the bridge priority using the command STP priority, then we give it a value. This bridge priority has to be a value that is in multiples of 4096. So that's why we are using 8192. So before we configure the priority, we have to undo what we had done earlier, STP root primary, by using the command undo STP root. So let's do that on S1. So on S1, we can do, let me clear. We start by undoing. So undo STP root. So after that, we set the new priority. So STP priority 8192, like that. Then I can do now the same here. On S2, I can do STP undo STP root. Then I can do STP priority 4096, which is the default. So with that configuration, because this guy has a smaller bridge priority, this guy is going to be elected. He's going to be elected as the root bridge. So let's use the command now. On we can even do it here to confirm. So you can do display STP brief. Good. I really wanted this to show up. So I want us to look here. So of course, when you see that the role of all the interfaces are designated, it means that this guy is already the root. But look at the STP state. So STP takes some time to transit between states, from discarding to listening, then listening to learning, then learning to forwarding. So before these designated ports go into forwarding state, it has to wait for the forwarding delay. Forwarding delay is 15 seconds from listening to learning, then again 15 seconds from learning to forwarding state. So that is very important to remember. So now, if I run that command again, display STP brief, look at it. So now the ports have transited from learning to forwarding. So now actually STP S2 switch 2 now is actually the root bridge. And you can also confirm that by doing display. So display STP, just display STP like that. So look here, what is this bridge ID? The bridge ID for this bridge is that. Then what is the root bridge ID? That one, 8A. So you're seeing it's the same. So when it's the same, it simply means that this device is the root. If we go to S1 and do display STP, now look at the bridge ID. So the bridge priority now is 8192 because we changed the priority. And if you look at this row, you can see that it's no longer the bridge. So that's how you can alter the election on who becomes the bridge in order to optimize the operations of your network by changing the bridge priority. Okay, so I hope that is clear. We can now go to the next step. So let me see. Okay, so now we want to, let me see. S2 has become the new root bridge. Okay, good. Here, we want to shut down the interfaces on S2, 009 and 0010. We want to shut them down. So what happens if the root goes down? So that is what we want to simulate. Okay, so S2, we know that S2 is our root bridge right now, but we want to shut down those two interfaces. So int 0/0/9, we do shut. Then we also go to int G0/0/10. We also shut it down. So when we shut it down, look here, if I do display STP, you can see that because the root bridge has gone down, this bridge, it takes some time. Let me just try it again. Because of the delays, because of the maximum age, the maximum age has to expire. So bado haija expire. Unaona maximum age lazima it take 20 seconds. So that's the reason why. So we wait a little bit. It's 20 seconds over. Good. Let's see now. Good. Not yet. 8. Okay. Let me be a little bit patient. Okay, let's see. Okay. Kwa nini 20 seconds imekaa hivyo? Okay. So as that time, okay. So as you can see here, once S2 goes down, then if you do display STP, then S1 is going to be the new root. So mine is taking a little bit, I don't know. Let me see. I'm wondering why it's not changing. I think it's more than 20 seconds right now. Wow. Okay. It was supposed to change, but it's not changing so far. I don't know why, but we can look at that a little bit later. So the highlighted lines in the preceding information indicate that S1 becomes the root bridge. So that is what is supposed to become, to happen when S2 is faulty. So after that, we are supposed to re-enable the interfaces that we've just shut down on S2. So let's re-enable. Let's give this a last try. I don't know why it's misbehaving.
Hello.
Yes.
Can you confirm? Did you switch off S2 or S1?
I switched off the interfaces here. Display.
Okay.
Yes, it's shut down. So I'm just wondering why it's taking too long for the other one to pick up. Display this. It's shut down. So I really don't know why S1 is not picking up, because it's supposed to pick up as the new root. Or am I using, let me see, display STP brief. Oh, I see. Maybe it's because it's the only switch, so no election is being conducted. That's the reason, actually. I'm sorry. So it's okay. So let's move on and undo the shutdown. So undo shut on S2, undo shut, and then we go to int G0/0/10. We also undo shut. It's because it's the only switch, so no need for election. So that's why we can't see that. So let me quit. So now the next thing we are supposed to do is to control the root port election. So if we do here display STP brief on S2, so this guy is the root, but on S1, let's look at S1. Display STP brief. So we can see right now 009 is the root, 10 is the alternate. So we know that in choosing the root and which one to block, we normally use the root path cost. But if two paths offer the same RPC, the same path cost, like in this particular topology, they offer the same root path cost. 009 and this one, they offer the same path cost. So if they offer the same, then the only thing you can do to alter, to change which one becomes the alternate and which one becomes the root, is by configuring the priority of the ports. The priority of the port. It's important to note that when you are changing the priority, you have to do it on S2 and not S1. So you have to do it on the other switch and not this particular switch whose ports you want to alter. So how to do that? You come to S2. Let me clear this. So you come to S2, then go into, for example, int G0/0/9. Then you do STP port priority. So we want to configure this with a higher value than 10, than interface 10. So int G 0/0/10. So for 10, we want to configure it with an STP port priority of 16. So whoever has a smaller port priority value will now become the root port. So on S1, look, if I do this command again, display STP brief. Let me just give it a second. So you can see now 009, by changing the port priority on S2, 009 has become the alternate and 10 has become the root, unlike what it was here. So now it has changed. So that is how we change the port roles whenever we are required to. Okay. So after that, the last thing I think that we are doing, run the display STP brief to see the roles. I think we've already seen that. Aha. So now we want to shut down 10 on S1. Remember, 10 is the one that is the root right now, so it's forwarding. So we want to shut it down and see how the port role of 9 is going to change. So let's do that on S1. So on S1, we get into int gigabit 0/0/10, like that. Then we shut it down. So shut. So the other advantage about STP is the fact that it can re-enable blocked. So as it is, before we shut down 10, this one was blocked, 9 was blocked. But if this goes down, this one that is forwarding goes down, then this one is going to be re-enabled. And that is what we've just done. So we've shut down 10. Now let's do display STP brief. And you can see that 9 has been re-enabled. It's still on learning state, still transiting through the STP states, but indeed it's going to forward data in a short while. So that's the other strength for STP. It can be able to detect when certain links go down and therefore be able to re-enable the ones that had been blocked. So they act as backup actually. Okay, so after that we are supposed to re-enable the shutdown interfaces on S1 and also undo the port priorities. We undo the port priorities on S2 so that we can go back to the previous port roles. So let's go to interface gigabit Ethernet 0/0/10. Then we do undo shut. Then here we get into that and do undo port STP port priority, STP port priority. Then we go to int 0/0/9. Then interface 0/0/9, and we also undo STP port priority, like that. So if we do that and come and check the port roles here, then 9 will be the root, and so display STP brief. So you see after removing the port priorities, now we have 9 as the root and 10 as the alternate. So that is really, I think, the last thing that we were supposed to do in this particular lab. No. We have the cost. So let me talk about the cost. Now you can also, other than changing the port priority, to change the port role, the role of the port, you can also change the cost. I said that the default cost for Huawei equipment is the .1T. In .1T, for example, if I do display interface G 0/0/9, STP interface. I'm supposed to do STP. STP interface like that. You can see that for port 9, the port cost is .1t. We've not configured a manual cost, and right now the port cost for .1t for 1 gigabit interface is 20,000. But now we can change this port cost so that this role can change, so that port number 10 can actually become the root port. So if we increase this port cost to a value beyond 20,000, then this port is not going to be elected as the root. Okay, so let's do that. Control C to get out of this list. Then let's go into the interface. So right now, if we do display STP brief, we can see that 9 is the root. So we want to change its cost. So we go to int g 0/0/9. Then we do the command STP cost. STP cost. Then we can enter 200,000. So 200, 1, 2, 3, 200,000, like that. So now, if we do that, if I quit and I do display STP brief again, you can see that by changing the port cost, the role has changed. Because this one has a smaller cost, it has now been elected as the root. It is still in discarding state because the state is still changing because of the forwarding delay. So if I do it again, you can see the root port now is in forwarding state. So ladies and gentlemen, that is all about the STP lab. That is what we are supposed to learn in this particular lab. I hope it has reinforced your theoretical knowledge about STP, and you've seen it live in terms of how it really works on a smaller scale network actually. Okay, so anyone with a question or suggestion? Anyone with a question?
Excuse me.
Yes.
What happens when you change the port priority, the one that has 128 dot a certain number?
So
priority of
let me just do it again. Display STP interface G0/0/9. So we have this. It's called the port identifier. The port identifier is a combination of the port priority and the port number. So there are two things that can decide who becomes the root and who is blocked when we have two links that offer equal path cost to the root. So the first thing that can change, can change who is blocked and who becomes active is the bridge identifier. No, not the bridge identifier, is the cost. So the cost is used as the first thing. So unaona kama hapa tumechange cost ya hii port ikuwe 200,000. We've configured it to 200,000. So 10 iko na better cost because cost yake ni 20,000. So 10 ndio itakuwa root, hii itakuwa alternate. But if they offer the same cost, 20,000, 20,000, then the next thing that will be looked at is the bridge identifier. Not bridge identifier, port identifier. Whoever has a smaller value, kama bridge priority in the same, then it goes to the port number. The port number cannot be the same. So that will be the tiebreaker. So sijui kama nimekujibu.
Yeah.
Exactly. So they're simply used for electing who becomes the alternate, who becomes the root port. Okay.
Karith,
Yes.
haujanijibu ile ya nini MAC address. Umeenda port number.
Unapotea
We have
kidogo we.
understood. Nimesema
Uh-huh.
hujanijibu ile ya nini MAC address.
What was
The way
it?
you have just I was like, if you have the MAC addresses, how do you calculate the one now with the lowest? Like for the port number, of course, that was 9 and 10. Eh?
Okay.
So we take 9.
Yeah.
But now, how do you get the lowest in the MAC address?
Okay. If we do display bridge MAC address, we can be able to see the MAC address of a particular bridge. So let me quit and do again display on S2, display bridge MAC. So really, you know, MAC address is written in it's written in inaitwaje hexa, in hexadecimal. So the computer itself knows how to compare these two MAC addresses to know which one is smaller than the other one. So the computer does that calculation really. It really compares, just like you can have a value like 10 and 20. So that is what happens when the election needs to go to comparing the MAC addresses of each bridge. So have I answered your question? Yeah? Okay, asanteni sana.